Project number 2, probability distributions. To begin, go to your statistics projects file and go to the second sheet. We'll start by generating 500 numbers from each of 7 different distributions, 4 of which are discrete and the other 3 are continuous. The discrete uniform is like rolling a k-sided dice once and observing the number on the face. The Bernoulli is like flipping a coin once and counting the number of heads, 0 or 1, with the probability of a head being p. The binomial is like flipping a coin n times and counting the number of heads, 0 through n, with the probability of a head being p. The Poisson is like counting the number of events in an hour with an average of mu events per hour. The continuous uniform is like choosing a number at random between A and B, where each of the numbers between A and B are equally likely. The normal distribution is like choosing a number at random from a bell-shaped curve centered at mu, such that 68% of the numbers are between mu plus and minus 1 sigma, 95% of the numbers are between mu plus and minus 2 sigma, and 99.7% of the numbers are between mu plus and minus 3 sigma. Finally, the exponential is like observing the time between Poisson events. So if there's an average of mu events per hour, there's an average of 1 over mu hours per event. Okay, let's go ahead and choose a seed here. Now I want you to use the last 4 digits of your student ID. So I'm going to use 7303, but of course you're not going to use that one. Use whatever the last 4 digits are of your student ID. Now the seed is what Excel will use to generate pseudo-random numbers. Excel uses formulas, recursive formulas that start on some number and then generate each number in turn, which appear to be random but aren't truly random because you can reproduce the stream by using the same seed. Now if you don't choose a seed, Excel will choose one for you and you will not be able to reproduce those the same stream of random numbers. So you'll see how that works when we get to that point. So let's go to data, and you should see data analysis up there. If you don't, remember you have to go to File, Options, Add-ins, and then Go at the bottom and check the Analysis Tool Pack and then hit OK. You only need the Analysis Tool Pack. Alright, then it should show up. Okay, so we hit the data analysis, and we've seen here the descriptive statistics. We'll use that again. We used it last project. You'll see histogram. We used that last project. We'll use it again. Right now, though, we're going to use random number generation. Double-click that. Okay, open up the distributions box. You see here the uniform. That refers to the continuous uniform. The normal is the continuous normal. Exponential, you don't see in here. That's because it's easily gotten from a continuous uniform. I'll show you how to do that. The discrete is for the discrete uniform. There's the Bernoulli and the binomial, and then there's the Poisson. Now, the first one, discrete uniform, is going to use the discrete, and it needs this value and probability input range. This is the most complicated of the generators, so I'll go ahead and help you set this up. So what you need to do is tell Excel, and I've left a column here called X, or created a column here X for this purpose. We want 8 different numbers here, 1 through 8, 1, 2, and we can center these 2, and then use the lower right hand corner to get to 8. And then we need to also say what the probability is of each of these. And of course, if we're rolling a dice, then each of the sides have a probability of 1/8, so an 8-sided dice. So we'll say equal 1 divided by 8. And then we'll center that and drag it down. All right, so there, we set up what we need for the discrete uniform. So go to Data, Data Analysis, Random Number Generation. Now the number of variables is the number of columns, and we're only going to do one at a time, so this will always be 1. Number of random numbers, that's the number of rows that will be generated, and we want 500 here. And then there's our distribution, discrete, that's appropriate. Now the value and probability input range were the numbers and probabilities that we had there, that we typed in. Do not use the labels and grab that box like I've done here. Now the seed, they do not let you put in a seed here. I would if I could, but this routine does not let you put a seed in here, so Excel will choose one for us. Now output range, once in the circle, once in the open box. Remember, this is the upper left-hand corner of the output. There's just going to be one column of output, so we'll click right there, and then we hit OK, and we get 500 random numbers. Go ahead and hit center. All right, now let's create a named range so that we can make analysis easy for ourselves later on. Now use the label, so grab D uniform, Control Shift with your left hand, arrow down. You see, it helps us that Control Shift arrow down. It's cumbersome or tedious to scroll all the way down like that. So Control Shift arrow is very helpful. Right click on that information, say define name, and now I get rid of that period and the underscore because I have a hard time remembering exactly the order in which they go. So to make it easier for myself to remember the name, I just say D uniform without any space or underline. Now I want to scope it to probability distributions. In other words, I want the name to refer to this data, but only in this project. I don't want to be able to invoke D uniform from any other of the sheets here. So I'll scope it to probability distributions and hit OK. Good. Then I see up here, there's my D uniform, and I click it, and indeed it grabs everything. Now if you make a mistake, remember you have to go to Formulas, Name Manager, and it's usually easier just to delete the file or delete the name range and start over. We see here that we have 6 from our first project, descriptive statistics, and then 1 now that I just created. All right, let's do the Bernoulli. So go to Data, Data Analysis, Random Number Generation. So 1, 500. Now let's go to the Bernoulli. And the P is the 0.2. And now we can put our seed in here. Again, you're going to use your seed that you typed up there, the last 4 digits of your student ID. And mine is 7303. And then my output, I change to Bernoulli, or the B5, and then hit OK. All right, get a bunch of zeros, ones, go to Home, and immediately hit Center. And let's create a named range for that. Grab the label, Control Shift arrow down, right click, define name, and leave it Bernoulli and scope it to probability distributions. Good, and I can double check to see if that's working. Bernoulli, yep. All right, now I'm going to do the exponential with you, and then you can do the remaining 4. So the exponential now requires a continuous uniform. It's an easy conversion from a continuous uniform into an exponential. But first we need a continuous uniform on the range from 0 to 1. So let's go to Data, Data Analysis, Random Number Generation, 1, 500. Now this is the uniform, and you see the default range is between A equals 0 and B equals 1. Keep the same seed, and I'll change my output range and hit OK. Good. I go to Home, Center, and use 3 decimals. All right. And the exponential now is very simple. Say equal minus natural log, minus 1 divided by 3, the mean, whatever the mean is for your exponential, and ours is going to be 1/3, times the natural log, parentheses, of 1 minus the uniform, right parentheses. So it's minus the mean, which is 1/3, times the natural log of 1 minus the continuous uniform. Good. I hit center and 3 decimals, and I can double click it down. Good. That's right. And let's do a named range for that. Control Shift, arrow down, right click, define name, exponential, and scope it to probability distributions. All right, go ahead and do the other 4 on your own. Binomial, Poisson, continuous, uniform, and normal. Note that in the Poisson, they're going to ask you for a lambda, and that's just what we've been using. The symbol we use is mu. So put in a 3 when it asks for lambda. All right, save what you're doing. All right, go ahead and do those other 4. Okay, here are the results. And I made all my named ranges. I can go up here and open my name box and see that I have 7 new named ranges. Notice that when I scroll down, I go through my data, but I lose the headers. They become hidden from view. Here's a little trick to keep that from happening. Go to 5. Click on the row 5, go to View, and say Freeze Pane. Use the top selection there, and you see Excel puts a line in there, and now when you scroll down, the data, you scroll through the data, but the headers remain in place. That's going to help us out a lot when we start doing our analyses. Alright, so go ahead and save that. Let's scroll all the way down to the bottom and begin our analysis of each individual variable. Now we can hit the Print Preview button. Remember, open this up, check the Print Preview and print, and then the icon will show up. You can hit that. That way we can get our dashed lines in there and see where pages. I made a page break on 507, and you see the right page break there. Alright, what we're going to do here is do a descriptive statistics over here. Use the histogram, using the descriptive statistics tool, use the histogram tool to count the frequencies in the classes that we create, and then we'll insert a chart to actually do a picture of the histogram. So this is the descriptives tool, same thing we've used in the first projects. Go to Data, Data Analysis, Descriptive Statistics. Now we can type in D uniform, that's the named range I used, to grab all my data with the label. So I have to put labels in the first row, check that box. Output range, once in a circle, once in the open box, and I'm clicking on A510. Now we just need to click the summary statistics box. We don't need the confidence level for the mean. That gave us the margin of error, which is not useful in this project. And then we can hit OK, and there we go. We got 500 numbers. See the countdown there? And now let's use 3 decimals. Now let's blue and bold the mean. Use the format painter. We're going to do the variance this time in the min and the max. We highlighted the standard deviation last project. This one, when you're working with probability distributions, the variance turns out to be a little bit more useful. So we're going to do that variance. Now, this is based on the random set of 500 numbers. By the way, everyone's numbers are going to be different right here because they're random. right? They'll be similar, but and you'll see what I mean by similar in a moment. But and you can kind of look, eyeball it, and see that your numbers are similar to mine. But since they're random, the numbers will be different, and therefore the statistics based on those numbers will also be different. But we can calculate, these are the sample values, we can calculate the corresponding population values, and we'll do that right here. Hit center. Now I can use my format painter to get this, right? Now what are the population values? These are what I call gold standards. These are the values that the sample will approach, but not exactly equal. They'll get closer and closer as the sample size gets bigger and bigger, and this is called the law of large numbers. And what are those population values, or where do we get them? Well, there are formulas. Go to your formula sheet and go to the second sheet, and you can see here for each of the distributions there's a population mean formula, population variance formula, and a population probabilities formulas. So we go back to our file and we see, well, we see that the k plus 1 over 2 is the population mean for the discrete uniform, and k squared minus 1 over 12 is the population variance. And of course 1 over k is the population probability. So if you're rolling a k-sided dice, each of the sides has a probability of 1 over k of occurring. So go back over here. So this is equal, left parentheses, k is 8, right? So we'll say 8 plus 1 parentheses divided by 2. And we can center this, use 3 decimals, and make it red and bold. And this is equal to left parentheses 8 squared, you can use the caret above the 6, minus 1 parentheses divided by 12. Use our format painter. Alright, now we see, now everybody's red values will be the same. This is mathematics. So mathematics, the values will be the same for everyone. The sample values, again, will be different, but the point is, based on the law of large numbers, these sample values will be close to the population values. And as I said, the larger the count is, in this case it's 500, the larger that gets, the closer the blue values get to the red values. If they're not close, you know you did something wrong somewhere. Alright, now let's use the histogram tool to do some counting for us, counting frequencies. Now, I see that my minimum is 1, my maximum is 8. That makes sense because I'm rolling an 8-sided dice. So I'm going to start with a 1, a 2, and then go up to 7 because I want Excel to count the number of 1s, 2s, 3s, and so forth. And we always have to leave one of the categories off at the end, one of the values off, because Excel needs that for the more that it creates. So we'll go up here, and now we go to Data, Data Analysis, Histogram, and the input range again is D uniform. The bin range, now we have to grab the label, the bin, and grab all the way through to 7, since we had a label in the named range. So we click Labels and circle for the output range, open box, and then I'm clicking right across from the bin. This is in F510, and I hit OK. Excellent. Go back there and home and go to center, and you see I have 55 1s, 65 2s, and so forth. Now we can calculate over here the rel freq, and then I can use my format painter and get that. Do a total down here. Auto sum. Center it. Good. Now I want to say equal relative frequency. By the way, we're going to use relative frequency here rather than percent relative frequency, because just like using the variance is more appropriate than the standard deviation when you're dealing with probability distributions, the relative frequency is more appropriate than the percent relative frequency. So we'll say equal, grab 55 divided by 500 and lock it with the F4, because I'm thinking ahead. I want to drag my formula down, but I don't want the denominator to move while I want the numerator to move. So I hit center, and I can use 3 decimals and drag it down, and then do an auto sum, and then do a thick bottom border. Alright, now let's blue and bold these. These are the sample probabilities. Now let's calculate population values. We can just copy that population header over there. Now this is just equal to 1 over k according to our sheet. And that, again, like I said, that makes sense because the probability of each one of the outcomes is 1 over k, since it's a k-sided dice. So we say equal 1 divided by 8. And we'll center that and make sure it says number up there with 3 decimals. And we can drag it down. And then hit the auto sum at the bottom, center that. And put a thick line underneath there and make these red and bold. Alright, again, everyone's red values will be the same. The blues will be different, but they'll be close to the red values. And it looks like that's the case. Alright, now hit save. Now you may be tempted to change the more to an 8. But as we learned from in the first project, we will not be able to do our histogram correctly if they have all numbers here. They have to have at least one non-numeric character. The dashes will work, but we're not using ranges here, so there's no dashes. So we'll just keep this a more, and then after we do our chart, we can replace the more with an 8. Okay, so let's go down to an open spot and say insert, and we'll use a column. Again, use the very first one. The other ones are variations on a theme. So we don't need to get fancy. We'll just choose the first one. Right click, cut it, and I'm pasting it right there in 526. And then making the size, go to the left upper right hand corner, go to format, and make it 3 by 8.8. 8.8. That's going to send it right across the side there, but still fit right in on the page. Alright, good. So we're going to click there, say right click, and say select data. And this is where you have to have the more there or a dash somewhere, or else this won't work. Grab 1 through the more, lift up, move this out of the way. Hold the control key down with your left hand, grab the blue and the red numbers without the labels and without the total at the bottom there. They have to match up. Good. Now let's go ahead, change this series 1, call it sample, and then call the series 2 population. That's what it was. Okay. Good, and hit OK. All right, there we go. We're getting something anyway. Now remember, stay away from the center. Right? If you select that center accidentally and just move it ever so slightly, you may not see that you moved it, but all the formatting gets thrown off. So when I click on a chart to select it, I click on the right corner, stay away from the center. Now let's go to chart styles here, and let's go to the last one. Alright, I like to use the last one in all these. That seems to give us the best one. Alright, and I go up to the plus, and then we want the axes titles. Actually, we only need the vertical. We do not need the horizontal, so uncheck that. We want data labels. We do not want grid lines. We do want the legend, but we want it. Go to more options. We want it. We want it on the top, but we want to uncheck the show the legend without overlapping the chart box. Yeah, it doesn't look good at the moment, but we'll fix that up. All right, good. Let's save what we're doing. Right, now let's change the axis over here. Let's go from 0 to 20 by 0.05. That looks good. Getting there. Let's add the axis by adding tick marks. So go to major tick marks outside. Good. And let's go to number. Only use 2 decimals rather than a 3. And then go to the paint bucket and go to line and make sure it's a black line. Right? Black line. Good. So far so good. Let's go to the chart title. Go up in there. This is going to be D uniform. One N. And this is K equals 8. And then we can italicize to K. Go to home and hit italics. Good. Let's make this black and bold. Grab the whole thing. Okay, open up the color. Black. Looks like it's already bold. Alright, and go over here to this axis title. And this is going to be probability. And make it black and bold. Okay, again, you want to make, like we did in the first project, we're going to copy and paste these charts and just change the source data, so you want to make sure you get everything correct. Let's see, that probability. Right, we don't want to reproduce errors. Now let's put a border on this chart. Double click on the corner there. Remember, stay away from the middle. Go to border, say solid line, and it should give us the black because we've chosen black once already. Alright, there it is. Notice that the blue and the red, oh, one more thing. Let's double, oh, we can change the more back to an 8 now. And we can put the bars together. Double click on the bars, any of the bars. Let's go overlap of 0 and gap width of 50. Ah, that's nice. Okay, let's save what we're doing. So we see here that the law of large numbers makes the blue and the red bars close. The blues fluctuate randomly, and the red bars do not fluctuate. And we see the blues and the reds indeed are close. All right, very good. Now, sometimes when you'll see that some of the later charts, I use special characters in here, a mu or a sigma. Those are the only other 2 special characters. And you can get those by going to Insert, Symbol, and Greek and Coptic. If you open up that subset, go to Greek and Coptic. You see there's the sigma. And you scroll up a little bit. Oh no, it's down. No, same, up 1 row. There's sigma, and there's mu. Okay, let's do one more together. Go over here to 544. So we go data, data analysis, descriptive statistics. We're going to say Bernoulli. Labels in the first row. Output range. Right here at 544. Hit OK. Good. Now watch. I can use my format painter up here. I can actually grab even the population values. Go to home. Hit the format painter. Pop that in there. And then come down. Grab the population. Control C. Control V. Now we notice from our formula sheet here that the population mean is just P. The variance is P times 1 minus P. So I'll say here equal to just 0.2. And it should give me the format I want. And this is equal to 0.2 star parentheses 1 minus 0.2 parentheses. Alright, we see they're close, but not exactly equal. Again, your blue numbers will be different, but the red numbers will be the same, and the blues should be close to the reds. Alright, now 0 is my minimum, and my maximum is 1. Now, I start at the bottom when you have discrete numbers, and I usually stop one below the top, but there's only two numbers total, so I have to actually include the top this time. So I'll do that. And then up here, now I'll go to Data, Data Analysis, Histogram, and I'll say here Bernoulli. That's my named range with the label. Now I'll come down here and grab bin 01 with the label. The output range will be right next to it. Good. All right. So I see I have 387 ones and 113 zeros, and this more has a 0. Well, let's just move that more up to where the 1 is. Clear this out. Put a thick underline under there, and now we can do our total auto sum. Remember, we need to keep a more there for our chart to work. And then I can come up here now, take both of these, Control C and Control V. Good. So this is equal to the frequency divided by the total F4. And you know what? I'm going to go ahead and transfer this formula over here, or this formatting like this. Say Format Painter, and grab that. Good. And this is equal to, yeah, we can just drag it down. And then I do my auto sum, center, and I can put a thick line underneath there. Now the population values, go to our formula sheet. We need a population probability of a 0 and a 1. The 0 is just 1 minus p, and the probability of a 1 is just p. So this is equal to 1 minus 0.2, and this is equal to just 0.2. And we can sum it up. Hit center and thick underline. Good. We see the blue numbers are close to the red, but not exactly equal. We leave the more there. Right click, copy this chart, paste it down here, right underneath there. And then we can right click, say select data, grab shows me my old data right up there. Go down, grab the 0 and the more. Lift up, hold down the control key with my left hand, grab the blue and the red numbers, no labels, and hit OK. All right, now we want to go, we notice that the high one is 0.8, so I want to go maybe up to 1 over here by 0.1. So I double click this, say Format Axis, or right click it actually, go from 0 to 1 by 0.1. And we see it looks much better. We can change the series 1. We have to rechange or retype in there. Go to select data. Series 1 is sample. Series 2 is population. And then I can go up to the top, actually change the more to a 1 now. And this can be Bernoulli. And did I do that? No, not 2 L's, not 3. And this will be a P. P and then equals to 0.2. All right, excellent. That's done. Save it. Okay, go ahead and do your binomial. Actually do the rest, and I'll make a few comments in a moment about how to get the population values over here. The rest are pretty straightforward. The population means and variances are no problem, but how to use these functions takes a little practice, so I'll help you with that when we get to that point. So go ahead now, do your descriptives, set up your histograms, use the histogram tool, and then copy and paste your charts, set that up right now. Okay, here is the binomial distribution. Note that my minimum is 0, my maximum is 5, so my bins go from 0 to 4. And then there was a more here, and I kept the more there until I did my chart. Now, how do you get these population values here? I'm going to clear these out and show you how I get those. If you go to the formula sheet, you see we're going to use the binom dist function. Okay, so for this, I want the mathematical probability of getting exactly 0 heads out of 6 flips. So this is equal to binom dot dist, left parentheses, that's the number of sixes, or sorry, the number of successes. Trials is 6, probability is 0.2. Now the cumulative is either true or false. False gives you the height of the binomial function. Cumulative, if you say true, gives you the heights of all the at that value plus all the values before that. Now 0, there's nothing before 0. 0 is the smallest, so true and false would give you the same in this case. So we're just going to say false, so the false in here, left parentheses, good. And we see that the sample value, relative frequency, or sample probability is close to the mathematical population probability. Now for this one, well, we can just drag this down now. And you see there that we get the relative cell referencing does the trick for us. Now this is a little different. There's a 6 as a possibility, which we did not get. 5 was the largest we got. So we need to account for that. So we're going to say 1 minus 4 or less gives me 5 or more. Right? So I say equal 1 minus binom dot dist, left parentheses, and I'm grab the 4, comma again, 6 trials, 0.2 probability, and then we say true here, because we want to subtract from 1 4 or less, 4, 3, 2, 1, or 0. And so the true gives us the less than, or equal to the value that we clicked on 4, and 1 minus gives us then 5 or more. And we see that they sum to 1. Excellent. Now the Poisson works just like the Poisson dot dist works just like the binom dot dist. So I'll let you do that one. Notice again that my minimum is 0. I go to 7, so 7's my max, so I go from 0 to 6. And left more there. And of course I left the more there till I did my chart, and then I replaced the more with the 7. Now this is the Poisson.dist function, and false all the way down to here. And then we're going to go 1 minus Poisson.dist function of 6 or less, and therefore we have to put a true in there. Okay, and there's my picture. Now the C uniform, these are continuous distributions now. Notice I have ranges in here, and that the ranges overlap. 30 to 40, 40 to 50. Now continuous distribution, continuous values are such that the probability of getting exactly on one of these endpoints is virtually 0. So we don't worry about that when we go right up to the endpoint. If I were to go 30 to 40, 41 to 50, I'd be missing everything between 40 and 41 because there are numbers in that range. Now how did I choose the bins? Well, the continuous uniform goes anywhere from 30 to 100. I want to go by 10, so I see that my smallest is 30.051. I started at 40, therefore. And remember also that the ranges go from underneath. So 40 means 30 to 40, 50 means 40 to 50, and so forth. My max is 99.951. I stopped at 90. And one way you can double check to make sure you've got your ranges right is if you look at your minimum, make sure it goes in this range, the first range there, and then the maximum goes in the last one. And indeed it does. And again, they do overlap. All continuous ranges will overlap. Now, how did I get these probabilities over here? Well, let me show you how I do that. Clear contents. Okay, so the formula says that it's the upper minus lower divided by b minus a. This is just the area of a rectangle, actually. So this is going to be, the upper is 40, the lower is 30. Now I can click on the 40, there is no 30, so I'm going to say equal, left parentheses, the upper is 40 minus 30 divided by, now b minus a is just 120 minus 30, now, or 100 minus 30. I don't see any 100 here or 30, so I can just type in 100 minus 30. All right, now the next one will be 50 minus 40, and I have a 50 minus 40 over here, so I say equal, grab the 50. This way I can just copy the cell divided by b minus a, which is 100 minus 30. And then I drag that down now all the way up to here. And then finally I say this is going to be 100 minus 90. That's the upper is 100, the lower is 90. I say 100 minus, now I can click on the 90, divided by 100 minus 30. Good. And they total up. Okay, notice again that the blues and the red bars are close. The red bars are perfectly even at 0.143, level, I should say, and the blue bars vary randomly about that, but they're close, but not equal. And now again, that's the same for all the sample values in the population, mean and variance over here. So. Okay, now here's the normal. Again, we have ranges here that overlap and they come from underneath. So 35 means 30 to 35, 40 means 35 to 40, and so forth. Now how did I select my bin numbers, or the upper endpoints of the bin, of the classes? I looked at my minimum as 34, and I want to go by 5, so I start right above that at 35. My max is 65.969, so I stop right below that at 65. And then I label these 30 to 35, and I look at my minimum, and it goes in there. So, and the maximum fits in this range, so I know I've got it right. And again, they do overlap. The probability of getting exactly a 35 or a 40 or 45 is virtually 0. Now, how did I get these population values? Let's go ahead and I'll show you clear content. The exponential works just like this one, and so you can do the same thing with the exponential. Now, what's the function we use? The norm.dist. All right, this gives us area under the curve of a bell-shaped normal distribution. Now, I want everything to the left of 35, so I say equal norm.dist, left parentheses, 35, comma, now 50 is the mean, comma, 5 is the standard deviation. Now I have to say true, because this gives me the area under the curve. If I were to say false, I just get the height of the curve, which is not a probability. We always need to say true here when we're calculating probabilities. All right, again, I see it's close to my sample value. Now here I want the area under the curve between 35 and 40. So the way to do that with a function that gives you everything up to a certain point is I do everything up to 40 minus everything up to 35. So I say norm.dist, and I can say 40 right here, comma 50, comma 5, comma true. And then minus norm.dist, left parentheses, I grab the 35, comma 50, comma 5, comma true. And then I drag that down. Finally, I need everything greater than 65. So to get the area under the curve to the right of 65, I need to take 1 minus the area under the curve to the left of 65. So I say equal 1 minus norm.dist, left parentheses, grab the 65, comma 50, comma 5, comma true. And that ought to do it, and it sums to 1. Great. And I get my nice bell-shaped curve there. Notice this one's flat, uniform. This one's bell-shaped. And finally, for the exponential, we want to go by 0.4. I know my minimum is close to 0. You can see up there that it's not actually 0. And then I go to 0.8, 1.2, and my max is 2.421, so I stop at 2.4. And I see my ranges here. Again, they overlap. I see that my minimum goes in that range and my maximum falls in this range. So you're going to use the xbone.dist function. Now they're going to ask you for lambda, and when lambda is 1 over mu, our mu is 1/3, so 1 over 1/3 is just 3. So you're going to put 3 in there for lambda and these xbone functions, and they work just like the norm.dist function did. Okay, you can review everything to make sure that your answers are correct. We're going to work on the central limit theorem. We have one more thing to do. Here, I'll save this, but you can go to your probability or the statistics project solution PDF file and see just what the solution to your project is. So scroll down here. This is project 1. Let's go to project 2. Okay, here. That's all our data. Okay, there's the discrete uniform. There's the Bernoulli, binomial, Poisson, continuous uniform, normal, and exponential. So use this to check your answers. Okay, recall that the central limit theorem states that the mean of a set of observations from any non-normal population will be approximately normally distributed with the mean equal to the mean of the non-normal population and the variance equal to the variance of the non-normal population divided by the sample size. So we're going to use, furthermore, that the approximation gets better as the sample size gets larger. So we're going to use the Bernoulli distribution to illustrate the central limit theorem. To that end, we're going to flip the coin, which is a Bernoulli distribution with p of 0.5. Flip the coin 10 times per set, and we're going to do 300 sets. So let's go ahead to begin with. We can expand. We have set 1 through set 9, but let's go all the way over to set 300. Takes a little while to scroll over there. All right, there we go. And come on back. Now, we're going to use the rand function to randomly generate our coin flips. So in here we can say equal if RAND, left and right parentheses, that's a rand function. It's going to randomly generate or choose a number between 0 and 1, comma, value of true we want it to say head, and value of false we want to say tail. And we have to put those in quotes. So equal if rand, oh, so I forgot something. If this is greater than 0.5, call it a head, else tail. Good, that's a tail. We can drag it down over here. And then watch what happens when we hit F9. F9 will cause the rand function to generate new random numbers, and we get, therefore, a separate or a new set of heads and tails. Good. Now, the mean of this Bernoulli is actually just the proportion of heads. If you think of a head as a 1 and a tail as a 0, or think of counting or taking the average number of heads that you get, it would be the proportion of heads. Ones and zeros, the average of the ones and zeros will give you the proportion of the ones. So we can say here equal count if, left parentheses, now we need our range, I'll put a count, if, grab our range here, and then comma, head, and then divide this by 10. So this is the proportion of heads. Number of heads divided by 10. Good. And that's Use 1 decimal and put a thick underline there. Now I can take this then and drag it across for the 300. Alright, we can go back. Great, and we can hit our F9 and see that we get new data every time, and it recalculates our proportion heads or our mean from the Bernoulli distribution. Alright, save that. Alright, now down here, the sample mean of the 300 proportion heads, we can just use the average function. Grab this whole thing. Little tedious to get all that. Alright, right parentheses. Good, and we can center these and make it 3 decimals. Good, now I can drag this down. I'm going to get nonsense, of course. But now I can say var.s and then just move the box up. Good. Alright, save that. Now the population mean and variance, population mean is equal to the mean of the Bernoulli, which is just 0.5, and then the variance is equal to the variance of the Bernoulli, which is 0.5 star, we can grab this, the mean star parentheses 1 minus the mean, divided by the sample size, which is 10. We flip the coin 10 times for each of the sets. Alright. Alright, notice that then, let's blue and bold the sample values again like we did before, and then red and bold the population values. Blue and bold values will be the blue values will be different for everyone. The red values will be the same. And notice how close but randomly different from the red values, the blue values are. See that when we hit the F9 over and over? Alright. Let's go ahead now and we can calculate a histogram or frequencies, and then we'll do actually a chart. So now we want to go from start at 0. The possible values for the proportion heads are 0.0, 0.1. Out of 10 flips, we go all the way to 1. That's the most you can get. You can get 0, which would be 0 heads out of 10 flips, or you can get all heads out of 10 flips and everything in between. Alright, now for this I want to show you a new way to count frequencies that doesn't require you to use the histogram tool. And this is called array functions. So you're going to grab this whole range here and say equal and say frequency, left parentheses, grab all the way up to 0.9. Oh, sorry, no, data array. That's the bins array. We got to grab all our data again. A little tedious. It was all up to 300. we go, comma, let's go back there. And then now we're going to grab the first 9 out of 10, not to leave the last one off, and right parentheses. Now Control Shift with your left hand and enter. Right, look at it, puts the little squirrely brackets around the formula in there, and each of the cells has that formula. Okay, now we can total up down here using the auto sum, center it, and yeah, save what we're doing. And see, when we hit F9, now the frequencies are calculated on the fly. Excellent. So let's do sample probabilities now, and that's just relative frequencies again. So we grab the frequency, divide it by the total, lock the total. And let's go ahead and make all these 3 decimals and center. Now we can drag this down and sum it up independently to make sure it's 1. It is. Put thick bottom border, make this blue. These are our sample values. Hit F9 and see those are working, changing. Good. Now the population, we have to use the finite population correction factor for this. So we'll say equal, but it's the area under the curve, right? So say norm.dist, left parentheses, grab this one, plus 0.05, comma. Now the mean is the 0.5. Standard deviation is the square root of the variance, comma, true. All right, good. See, it's close. Now here we want to get equals the all the way up to 1 plus the correction factor minus 0 plus the correction factor to get the area in between those. So we say norm.dist, left parentheses, x plus 0.05, comma, mean, now let's lock it, comma, square root of the variance, lock that, right parentheses, true, minus norm.dist, grab the one before it, plus the correction factor, comma, mean, lock that, comma, square root of the variance, locked, comma, true, and there, good. Now we can drag this all the way down to the next to last one, and you see it doesn't like, or the format didn't stay fixed. So now I can fix up the format with the format painter. Good. And finally we say equal 1 minus norm.dist, the 0.9 plus the correction factor, comma, mean, comma, square root of the variance, that's the standard deviation, comma, true. All right, let's see if it sums to 1. It should. Ah, it does. Good. We'll hit the thick underline and then make these red and bold. All right, save what we're doing. And we hit F9. Good. We see the blue values are close, the sample values are close to the population values. All right, let's do a chart now. Now, in order to do that, we should put a more here first. All right, same issue when we do a chart as we had before. You have to have dashes in here. Okay, so insert. Let's insert a scatter diagram. Okay, cut this and we'll put it right there. And let's make it 5 by 6.83. 5 by 6.83. Make it nice and square. Okay, save our work. Okay, right click, say select data. We're going to add. Actually, we don't do that. We don't need to do that. We can do the default like we did before. Click up here, grab the range of heads all the way over there, and then hit the control key and grab the blue and the reds. And we can change the series 1 to sample like we've been doing. Series 2 to population. And hit OK. Alright, it's a start. Now we can change the more to a 1. Okay, save. Click on the corner. Remember, stay away from the center. We don't want to accidentally move the inner box and mess up our formula or our formatting. Now let's go to the paintbrush and we'll go to styles again and go to the last one. And then go to the plus button. We want the axis titles. We want both of them. We do not need data labels. We do like the grid lines this time. Put the legend and let's put it at the bottom. Alright, looking good. But we can make it look even better. So let's go up to the chart title and type in this long title here. Distribution. Put it up inside there. Distribution of proportion heads, enter in 300 sets of 10 coin flips. And we can make this bold and black. Alright, down here, this axis title, we can make this proportion heads, and we can grab it, yeah, black and bold. And then over here on the y-axis, make this probability. And make it black and bold. Good, save it. Now let's change the ranges down here. Go to the x-axis. And we want to go from 0 to 1 by 0.1. Alright, and let's put some tick marks in there. Major tick mark type outside. Go to the paint bucket. Make sure that the line is black. Solid line. Good. Let's go to the right here. Yeah, we're going to go 0 to 0.3 by 0.05 is good. Let's put the tick marks in there. Major tick mark outside. And number, we only like 2 decimals on that. Alright, we're getting there. Save it. Let's put a border on the outside. Double click on the edge there, say border. Solid line should come up black, yeah. Good. Now let's change that red line. So click on the red line there, and then go to Paint Bucket. Want solid line. Let's go the red color. That's the color that it was. I don't know why I changed it. Go to the width up to 3. And then go to marker. Marker options, and let's get rid of the marker. We don't really need that in there. Alright, save it. Let's go to the blue line now. Double click on that. This is the sample line. Let's go to the paint bucket. Solid line. Now we don't need that. Yeah, solid line. Make sure it's blue, which is up there, and then make it a 6 point. And then go to the dash type and use the second one there, the round dots. Okay, I didn't like that. I only chose one little aspect of it, so go back. Yeah, make sure when you click on that, it clicks all of them together. You can click away and then click back on there. Oh, good, there it is. So paint bucket, solid line. Yeah, it's the blue. Go up to 6. And then the dash type, use the dots, and then go to marker, and let's get rid of the markers that are on there. Alright, now I'm going to open this up a little bit so we have some room. And now watch what happens. Yeah. Alright, you see that blue line gets close to that red line. Alright, now there's a few points I want to make here. The law of large numbers means that as the number of sets increases, so we have 300, but as those numbers of sets gets larger and larger, the sample curve, that is the blue curve, gets closer and closer to the red curve. See, it's pretty close with 300. Also, then now the central limit theorem would states that as the number of coin flips increases, we have 10, the curves become more bell-shaped, both of them. But you can see just with 10 flips, they're both very well approximated by a bell. Or they look like good approximations to a bell. Now, actually, let me fix this axis over here. It didn't seem to want to stay at that. 0 to 0.3. Yeah, by 0.05. Okay. Good. Save that. Yeah, that way, whenever we hit F9, we continually get the 0.3 over there. Very good. I was going to say, note that there's a rule for a Bernoulli distribution that n times p and n times 1 minus p have to be greater than or equal to, both have to be greater than or equal to 5 for the normal approximation to be appropriate. And you see here that with 10 coin flips, that's exactly the minimum case, because 10 times 0.5 and 10 times 1 minus 0.5 are exactly equal to 5. So we see that that rule does make a lot of sense and is appropriate. All right, and that completes project number 2.